All right, we're looking at volumes of revolution in this video. Sometimes they're called solids of revolution. Basically, what you do is you graph a function. So if you look at the graph of y equals x squared, it's going to look something like that. And then you sort of imagine going into 3D land and just like sort of wrapping this function in 3D around the axis, right? It makes this like wacky shape, sort of like a funnel or something here. And it'll eventually just make this whole like surface. Obviously, it's very hard for me to draw this in 3D, but that's what it looks like. And we can calculate the volume of this thing. So there's a formula for it. So the volume is, and it depends whether you're going around the x-axis or the y-axis. So this is the formula for going around the x-axis, and then it's sort of reversed to the y-axis. Y squared dx, and y would be the function. So it's pi integral from a to b y squared dx, and y in our case is x squared. That's pi integral from a to b. X squared is y. We're going to square that and go dx. And this is pi. I can actually put in what a and b are as well. It's from 0 to 5, so we'll just pop that in here. 0 to 5. So this is x to the power of 4. So this is from 0 to 5. This is pi. It's x to the 5 over 5 from 0 to 4. We could have done this on the calculator, actually, but it's 4 to the 5 over 5. Take 0 to the 5 over 5. So yeah, we can just basically figure out what that is. So 4 to the power of 5 all over 5. So it's 1024 over 5 times pi. And this is cubic units, so it's units cubed. If you want, you can get an approximate for this. So times by pi, and then here s to d. There we go, 643. 643. Okay. Now, find the volume of this. So this is y equals x. So there it is, y equals x. We're rotating through the y-axis. So we're actually coming around the y-axis here. And this should be between 0 and 1. Okay, so we're going to go up to 1 on the value here. And you might be wondering, well, what shape does this make? We probably know this shape. Like an ice cream cone kind of shape. So that's what we're trying to calculate the volume of. Okay, so let's see. The volume is pi, the integral from c to d of x squared dy. Now, luckily, this is just y equals x. So x is y. So that's y squared dy. Now, when I say c to d, I mean the two y values. So this is y equals 0 to y equals 1. You've got to be really careful about that. 0 to 1. And this is pi. You got y cubed over 3 from 0 to 1. And so that's just pi times 1 cubed over 3. Take 0 cubed over 3. Or in other words, it's 1 lot of pi over 3. Pi over 3. We can get an approximate for this. So whatever pi over 3 ends up being, it's a third pi, which is 1.05. Okay, cool. Now, how do you know that I'm not just completely lying to you? Well, there is a formula for volume of a cone. So yeah, this is the formula here, pi r squared h over 3. So the volume would be pi, 1 squared, and h is 1 as well, all over 3. So that's pi over 3. So yeah, we get the same formula for volume of a cone. You can actually prove this formula using volumes of revolution. So I'd encourage you to do that as an exercise. Okay, we can also do between two functions. So essentially what you want is the integral of the top minus the bottom squared. Let me just make sure I've absolutely got that right. No, I lied. It's the top squared minus the bottom squared. Okay. And we're going around the x-axis, so dx. And then here we're going from 0 to 1 because it's sort of like x is 0 to x is 1. Function on the top is root x. And then the function on the bottom is x squared. And I think we need a pi out the front. Okay. So this is pi. And then we're going to go from 0 to 1. Root x on the top, so we'll square that. And x squared on the bottom, so we'll square that. Now, I've learnt my lesson. I'm not going to try and do this integral by hand. Let's do it on the calculator. So root x squared, take x squared squared from 0 to 1. And screw it, let's put a pi in front as well. Do the whole calculation. There we go, 3/10 pi. Which roughly equals, and we can hit S to D there, 0.942 units cubed. Now, what's this shape going to look like? It's sort of going to look like that, and it'll like sweep around. So, yes, what would it look like? It would look like another one down the bottom. I'm trying not to just draw Pac-Man here, but it would look like that. It's very difficult to draw. But yeah, it would almost look like a bowl shape. Yeah, very funky shape indeed. Oh, there it is. It's a bowl shape. Okay, wonderful. There's some examples you can do with this in the real world. So like a very common assignment for spec is to find the volume of a wine glass. And so you sort of model this wine glass and then do volumes of revolution around it. And that, yeah, you can imagine anything that's sort of symmetrical just by rotation. We've now essentially got volume formulas for them, which is really cool. Like, who would have thought we could calculate volumes like this? The other thing that I'd also just want to do is prove the volumes of revolution formula. So essentially, if we have something like this, what we can do if we have like a function like that or whatever, and we would like the volume of revolution between those points here. You can like slice it up into a whole bunch of cylinders. So much like how we slice it into rectangles, it's just instead of these being rectangles, they're being cylinders. Bit hard to draw the cylinder, but hopefully that gives you the idea. It's like a, there's the other bit of the cylinder. So yeah, lots of little cylinders. So what's the formula for the volume of a cylinder? It is, well, pi r squared for the radius times the height of the cylinder. Now, when I say height, I don't mean the height, I mean the horizontal height. So like, there's our cylinder. The distance from the center up to the top will be the radius, and then the distance across here will be height. So essentially, how do we get this radius? This radius is the height of the function at any point. So whatever the radius here is how high the function is up. So each cylinder will look like that. So I'm going to say that if we're splitting it up into a whole bunch of cylinders, I'm going to call this length here dx. Little distance in terms of x. And it's always going to be the same because I'm always splitting it up. So the volume there is pi r, well, instead of r, I'm going to have our function squared. I'm going to be timesing it by the height, which is dx. And I'd really like to be doing all this and add them up. So really, when I'm talking about adding them up, I want to sum pi of x squared dx. But as that goes to 0, sums become integrals. That's like our definition of an integral. So the volume is this sum bit will become an integral of pi times the function squared dx. I think the volumes of revolution formula pulls a pi out the front, and instead of a function, it calls it y. But that's where the formula comes from. It's essentially, rather than a bunch of rectangles, we're doing a bunch of little cylinders.